let us read your papers for this topic.
Hi, dear.
No paper yet. Okay.
Hi, Arturo.
We will wait for. So please, please, we go to the next talk. Either here, Arturo Vieiro, Escape Times Across the Golden Contours and the Evolution of Approximant Islands. Here, so we see your presentation. So, please, Arturo, can you begin? So,
We cannot hear you.
so now we see only Berthold.
Arturo, we don't have a sound from you.
So, where is Arturo?
Here.
We saw a presentation, but not a sound. So what happened? So presentation is here, but where is the author? Neither presentation, neither author.
Can you hear me? Can you hear me?
Yes.
Now, yes?
Yes.
Oh, sorry for that. I had some problems. Okay, no, sorry. No, can you hear and can you see my presentation also? No.
Yes.
So sorry for that. So, well, I want first of all thank the organizers for inviting me and to give this talk here today. I'm going to present some results on escape time across Golden Cantorus. And these are quite, let's say, we started these studies a long time ago during the thesis, PhD thesis of Narcís, but we finished some works now and we are trying to publish things in this area. So I want to present this here today. This is a joint work with Narcís Miguel, who was my student and also Carla Simo student, and also Carla Simo collaborated, of course. Okay. So as I said, what we are going to do in this work is quite simple and a well-known problem. So essentially, we consider the standard map. This is a twist area preserving map here written in this way. This is the way we express it and we use it in computations. And what we want is to study how transport goes in the standard map when we look for transport properties. We look for parameters k, this k here, larger than the well-known constant Green's constant. And for those who, I mean, this is well known, but I simply recall that for values of the parameter less or equal than the Greeny constant, there are rotational invariant cores in the cylinder that do not allow points to diffuse along the cylinder. And for values of the parameter larger than this Greeny constant here, points are allowed to drift along the cylinder. So this parameter plays a key role in the global dynamics. Let's say there's a change in the global dynamics. Okay, so it's also well known that this parameter Greeny is an estimate of the parameter where the last invariant rotational curve there is destroyed, and this last invariant rotational invariant curve in the cylinder has a frequency is known to have frequency golden. So these are well-known facts. So in order to investigate this, our goal is to investigate the dynamics near this invariant curve and near the breakdown. So in order to do that, there is a nice theory which is essential. I mean, the idea is quite clear. What you want to do is to magnify or to zoom in regions near the last invariant curve. And so what we, in mathematics, we use this renormalization idea that was already done by Greeny and McKay. This is a nice theory that is quite a standard nowadays and a beautiful theory on renormalization. And what it does is essentially what I said. I mean, if you consider a twist map, you denote, you consider the leaf of a twist map into the plane, and you look for the sequence of best approximants to the rotation number that you have in the of the curve you want to approximate. You want to look to zoom in around. And in the case of golden, these are quotients of successive Fibonacci numbers. We are going to use that later. And what you do essentially is you scale the phase space around the last invariant curve. So to zoom in regions, in treatable regions where you can see details of the map. The proper choice of the zooming, of the scalings, this scalings lambda here that appears, will be explained later in detail, because I'm going to iterate this operator. So, but it's essentially related to the properties of the rotation number rho that you are playing with. So moreover, you start with a map on the cylinder, and you want that all the renormalized maps, when you apply the renormalization operator to your map, you obtain another map, and you want to guarantee that this is a map on the cylinder. And this was the reason why this renormalization operator was defined on commuting pairs of orientation preserver, this geometry of the plane, because you want to commute with this R that appears here. Okay, more essentially. And so let me simply recall how it works. I mean, what you do is you play with a renormalization operator that depends on some parameter m. This m will be chosen according to the arithmetic properties of rho, of the rotation number. For us, rho will be golden, as I said. And you play with this pair of commuting pairs, of commuting UT maps, and you scale in that way. And what you want to this is the way how you scale and how it acts the operator. And this allows you to investigate the dynamics near the last invariant curve. And in the case that we are playing with, we have to choose U and T, this commuting pair, to be the R that appears here, this map here, that revolves along the angle of the cylinder, let's say, and this lift of the map of the twist map that we have. These are the classical choice that people studied in this setting. And you perform iterates of these commuting pairs using this renormalization operator that I defined here. And as I said, the sequence of m's that I'm going to choose to investigate near the invariant curve that I want should be always related to the arithmetic properties of the rotation number of the curve. And what one typically does is you write down the continuous fraction expansion of your rotation number. Then these m's that appear there are essentially related to these constants L that appear here in the continuous fraction. And for the specific case that I'm going to consider, that is the golden frequency, all these numbers are equal to 1. So what I have to consider to investigate near the last invariant curve of golden rotation number is the renormalization operator with parameter m equal to 1 always. Okay, so this is what I'm going to do. So I'm going to look at the dynamics of the renormalization operator with subscript 1. And of course, there are many known facts in this area. Not everything is proved, but almost everything is proved. And let me recall what is known. So first of all, well, this is something I already said. I need to study the normalization R1 of my maps MK. MK is the standard map with parameter K, and I'm going to look for K close to the greeny values. And the phase space of this renormalization operator that acts on maps is characterized by the existence of the fixed points, and it's known that it has a trivial fixed point, that is this one here, is this here, and this is an integrable map and is an attracting fixed point of the renormalization operator. And for this map, well, you can have periodic orbits, but all of them are parabolic, of course. Okay, so everything is rotating. And there is also a critical fixed point, which is the one I will be interested in. And this map, this critical fixed point is a map also, because it's a critical fixed point of the renormalization operator that has a critical golden rotational invariant curve. And it's known that this critical fixed point is of saddle type and only has a single unstable eigenvalue. And this single stable eigenvalue is approximately this number here. There are also elliptic orbits in the map, of course, and all the elliptic approximant orbits of RC, approximant will be explained later what I mean by that, but are, well, I can say now, I mean, these are periodic orbits that have a rotation number, one of the approximants of the golden frequency. And all the elliptic approximant orbits of RC have the same trace, okay? And this is this tau star that appear here. These are something that are known, and this is the picture. Then we have the critical fixed point that is of saddle type. This is the unstable direction in blue. And so this is the delta, the parameter. There are an infinite dimension unstable manifold. And the ratio of contraction is the largest, the dominant attracting rate is the delta prime, and is also known, is this number here. And there are also the trivial fixed point here. I mean, almost all these things are known, but maybe it's not known if this connects in that way or not, but essentially the local character is known. And if you take your map, standard map, and you iterate, you follow an orbit that more or less, you can imagine something like that. It moves in that way, and it crosses this infinite dimensional stable manifold. And in this for the parameter, when you have the parameter greeny, this is what happens. As I say, the existence of the point and these things were proved, some of them were proved by Mackay in his thesis over Mackay, and others were proved later in computer-assisted proof by Arioli, and the fact that that is saddle and this delta parameter only one stable dimension was proved by Koch, and so on. Okay, so here are the references. So, but let me just show what I'm going to do. What I'm going to do is first to show you iterates of the standard map under R1, and to do that I need to define the scalings. I simply compute some periodic orbits that I'm going to show. I'm writing here, but I'm going to show in the next slide also. And from these periodic orbits, I'm going to fit the position by a cubic, the position of some of them by a cubic polynomial. And this cubic polynomial will be used here. Is these parameters in the scaling lambda here that appears at the end. Okay, so, and moreover, I'm going to compute the distance between the elliptic and the hyperbolic, between two consecutive elliptic and hyperbolic fixed points of the same rotation number, and between the elliptic and the elliptic of the next rotation, of the next approximant to my rotation number. Okay, so this is what I'm going to do. And I'm going to show you the results. So here you have, for instance, the first iterate of the renormalization operator for my standard map, and the second, the third, there's all of them up to 16. And these are the orbits that I compute. I compute the elliptic one, the next elliptic one, the closest to the right elliptic one. So this give me the scale in x, this gives me the scale in y. This dx, dy that appear. And also I compute the hyperbolic points here in these ones. And for this, from these four periodic orbits, periodic points, I compute the cubic polynomial that interpolate, and this is the cubic polynomial that appears in this here. So every time I iterate, I do the same. I compute for the renormalized map the position of these orbits. I compute the cubic polynomial, and I do the same. So on, so on, so on, so on. Okay, and here what I'm showing you is the iterates of the standard map for the parameter that is slightly less than the Gurini parameter. So they should converge as expected to a regular map where no chaos is presented. So, and this is what we see in the last plot. We show in this gray color regular orbits. And here I do the same, but for some parameters, for a parameter k, which is larger than the Gurini parameter, and as expected, it goes to something that is quite chaotic. And indeed, if you compute one extra iterate of the renormalization operator, you cannot detect, at least with the precision we compute things, because we approximate regular orbit computing and the Lyapunov exponent. We cannot detect any irregular orbit, so it goes to completely chaotic map. So these are the iterates, and we see the details close to the invariant curve or close to the Cantor Aubrey-Mather set, Cantorus, that survives when you destroy the invariant curve for k larger than the Gurini parameter. So next topic I want to address briefly is how we computed a better estimate of the Gurini constant. And from the computations we did, we can do that. But in order to do that properly, we needed to investigate sequences on the trace and sequences of the traces that we have in the periodic orbit. And since I don't have too much time, I want to skip a little bit some details here. But essentially what we do is to consider these tau parameters where these are J1, J2, J3 are the order of the approximants that we are taking from the golden. So coefficients of Fibonacci and so on. And there are places where the trace of the one of the approximant coincide with the other one, and these are these numbers here. T34 means that the trace of the third order approximant coincide with the fourth order one, and so on. So this is the tau minus and 2 plus. I don't know why it doesn't appear properly here. I'm sorry. So investigating carefully numerically all these sequences of traces that we compute for many approximants up to here I shown up to 17. We were able to check, at least numerically, all these facts that are writing here, but that essentially say the following. That if you compute these places where these traces where the two lines coincide, and you compute the case corresponding to these places, the sequence of case, these are two sequences that have nice properties in the sense that they converge. The first one, the taus, converge to tau star, and the second one to converge to the k of Gurini. And the velocities of convergence are of this order, which means that we can use these sequences to compute this Gurini Gurini constant in particular. The right-hand part will converge to the Gurini constant. Okay, we are not able to prove all this conjecture, but at least to check numerically for the orders that we use, we are able to do it. And so the idea is to use these sequences, as I said. And these sequences, the tau part of the sequence converges to tau star in this with this ratio, and the k converges to the Gurini constant with this ratio here, delta prime over delta, and it happens that this is much faster, or a little bit faster than if you compute the constant for the k values of for a constant tau. So this is why we use this sequence. And in our computations, what we did is to compute these sequences up to the 35th best approximant of golden. And we need 50 decimal digits to do that, which is quite easy nowadays. And using also, take care because the period of the periodic orbits increases. And using the Aitken's accelerator method to get a better estimate, we were able to obtain 21st digits of the constant of the Greeny constant using this sequence. I mean, the idea is to iterate both sequences at the same time. You correct. You use you move j, and for each j you compute the taus that they intersect, and you compute the case, and you update. So this is essentially the idea. And the ratios that we observe numerically are very close to the expected values that are known to be these values. Okay. So, and we use this Greeny parameter that we obtain, because otherwise we cannot do these plots here. We use the approximation with 21st digits to show you these pictures here. This is more or less what we expect to be the critical curve. And let me tell you what I mean by that. We mean the following. I mean, if we magnify this curve near pi, and this is what we do here, because we display x minus pi and we put it in horizontally, we can see our these green dots here. Black dots here, black points, and also there are islands nearby that are magnified here. You can see some islands around. And again, if you carefully magnify things, this is the curve. And at least up to the scale of 10 to the minus 22, we can detect some islands nearby, but nothing else. I mean, maybe there are some Cantor, of course, but tiny. And the periods that we detect are of this size here that you have. Writing here. So there are quite a large periodic orbits, approximate periodic orbits that have frequency or rotation number, which is the quotient of Fibonacci's, and are of this period. Okay, so we believe that this is close to be the critical curve. Okay, so next I want to go to the last part of the talk, which is concerning these escape rates. And for that, we need to, with this picture suggests to investigate the islands. So we did some computations on the size of the islands, on the measure of the size of the islands. And here we displayed the size normalized by the scalings. Here is a normalization by the scalings of the renormalization that the renormalization provides. And if you scale properly, you see how this is the logarithm of delta logarithm of k minus k Greeny's constant. And we see many islands that are appearing nearby, and so on. And in the next slide, and so we see how the measure evolves. And in the next slide, I'm going to take a fundamental domain here from -9 to 10, and I'm going to show you the yellow, the blue, the red, the black, and the magenta islands in this from k tilde -9 to -10, how they evolve, and this is the evolution. Okay, so we can plot these tiny islands and see how they evolve with respect to the parameter. And this is important because we see that these islands, of course, have the typical behavior that invariant curves are destroyer. There are, I mean, the size oscillates and so on. The domain of stability changes drastically when you change the parameter. And this plays a role in the transport properties. And this is the key point of this work. So another object that is relevant for transport is the Mathers delta V. Delta W, sorry. And so this is essentially the flux or the area per iterate that crosses a turnstile. And the turnstile is created by joining by a line, with a line, the periodic orbits, hyperbolic and elliptic periodic orbits of the same rotation number. Approximate periodic orbit of the same rotation number. And here what we show is the Mathers delta V, normalized also, scaled by the scalings that we obtain numerically. And this is the behavior in the left. In the center, you see the behavior of the delta V, that the part of the areas that inside the islands, this island that I showed before, tiny regions. And on the right, the part that is in the chaotic region. And you see like an scaling also and beautiful properties that can be read from that. So let me move away because I need to finish in 2-3 minutes or something like that. So all these ideas allows us to understand a little bit how the escape rates behave. But on the, what I refer by escape rates, by escape rates, what I refer is writing here. I is the time that a point needs to escape from a region. We took a region in the cylinder between y0 and y1. We took points in the chaotic zone, and we expect that it leaves this region. This is what we do, essentially. It is expected from renormalization theory that the average of the escape times, this here that I will put here at the end, is expected to behave as a power law with some parameter b that is related to the scalings that I have in my domain. These are alpha, beta are the limit scalings that are related to the delta dx and dy that I was showing before, but in the limit. And from the renormalization, one expects, I mean, because you have this relation here, this implies that there should be a periodic function depending on log of delta delta logarithm of the increment k minus kg. And this function is expected to be, but we are able to plot it, and this is what I plot here. I mean, this is in the bottom. I mean, in the top pictures, we see the power law, and this is the estimate of the power law. I don't know why it doesn't appear. Probably, I don't know why, but sorry about that. I mean, here it should be B, and here it should be the average of B, and this is the B we compute. This B here.
Arturo, please finish.
Yeah, I'm finishing. So here is the periodic orbit that periodic function that we can obtain numerically, and we obtain an estimate of the B in the power law that is close to the theoretically expected one, which is delta alpha beta. That is that here that we plot this number here that appears in Mackay theory. So nevertheless, I want to finish now because I have to finish. With some comments, and okay, we are able to approach the breakdown until this a distance of this order, but we are still far from the limit, and nevertheless, computations for smaller values are still far from practical and very hard to do it. And but of course, if we were able to do it, we expect this to oscillate around a horizontal line. And probably the parameter that we estimate, this nk, should be closer to the Mackay estimate, but we haven't checked it because we are not able to do it. And on the other hand, these numerics that we are presented here, we believe, of course, it needs to be clarified which are the orbits responsible for the actual transport properties. But from these numerics, we see that the area that accessible to orbits changes because the area of the island that we were able to follow and to show changes. And of course, these changes of the islands are not monotonic, and everything. I mean, the area accessible is not monotonic, so this is how the transport properties changes according to this area, let's say. And we know that there is a periodic way, if you scale it properly, to represent these oscillations, and this is what we show in this plot, in this periodic function here. Okay, so just to finish, because I have to finish, of course, there are many other questions that we investigate a little bit and we are not able to do. First of all, it will be nice to know what can be said about the probability law of the escape. So we can compute histograms and these things, but we don't know which kind of law these iterates, these escape rates follow. We have also did some investigations on the parameterization of the golden rotational invariant curve when k goes to Gay-Greeny. There are previous results also by Orbera and Petrov, but we are investigating this a little bit more. And what is crucial or what is essential from the results that we show is that our numerics indicate that transport properties in the Cantorus might be described by a Markov process, where you have to take into account this chain of islands, the set of islands that play a role near the Cantorus. And the number of islands, the number of different rotation number that play a role changes with k, as we show in the previous slides. Okay, so I'm sorry for the late starting and so on. But
somebody have very short question and very short answer.
Okay.
I have A very ignorant question. Is it obvious by now that the golden ratio circle is the last to break down? I mean, everybody knows that, but is it true? Is it
You
true?
mean if there is a proof of that?
Yeah.
As far as I know, there is a strong evidence of that. And it should be a novel because
So,
this is
so
novel
you have
number.
tried KG for others?
Yes, for all. I mean, yes, of course. I mean, everything I show here is for the golden,
Yeah,
but any other novel number is the same, and we tried for others.
yeah.
And we tried also for numbers that have 1, 2, 1, 2 in the continuous fraction and these things also. Yeah.
At least you have no counterexample.
No, this is what they say. I'm not. I don't know if there is a complete proof. I think it's not.
Thank you once again. So we have to go